in to you in Mexico. I don't know how to do it. We use a system that is called Right Space, and where we can exchange very easily the material. I am going to probably commission Rizzo to open a file exchange place where we can put the classes and all these things.
Thank you.
In what? No. It has to be outside because they cannot participate in Brightspace. I tried to add their names and it doesn't work. Okay, so I am going to start from the very beginning, starting with the typical question of what is electricity and what is magnetism. And it may seem something a little bit stupid, but it's not. The important keywords of why or how to understand electromagnetic fields and finite elements are in definitions of electricity and magnetism. Okay. So I like to open it a little bit to the public, right? What is for you electricity, and what is for you? Let's start with electricity. So, and the way I teach normally is I use my tablet like this, right? And so, what is electricity? Speak louder because they can't hear you.
Flow of charges.
Flow charges. Flow of charges, you say. That is called current, not electricity. But that is a current. That's electric current. That's not electricity.
Power. Kind of power.
It's you're checking my notes from other time, huh?
No.
Well, it has to do with flow of charges, but it's not only flow of charges. Charges don't need to flow. So you can say flow, or instead of flow, interaction. Interaction of charges. Whether they move or not, it doesn't matter. So charges, you can say they interact, they move, or they are static. In any of those conditions, you have electricity, whether the charges are standing or static or they move. But there is something that is happening between them that is observable. So electricity has to do with this. But what is when we observe? What is what we observe out of electricity? Force. Force. That is absolutely number one thing, force. Force, as we will see today, it's related to the most important concept invented by humankind, which is money. Okay. We will relate force with money, and this is the way to understand Maxwell equations, electromagnetic fields, all these things is by understanding force. And force can be understood by understanding money, which I think everybody in the room or online can very easily relate to money. Now, for the Mexico people, if you are not understanding me, I am sorry. But if you have a question, you cannot formulate it in English, you can ask it in Spanish and we will translate it here. So, but I don't check the chat. So if any one of you can please check the chat, I don't know. I don't know how it goes. All right. So is the interaction of charges, whether they move or not, is one thing. Now, but we can observe it as force. Is there any other way we observe electricity? Well, I'm pretty sure you all are in a place that has light. I'm sure that you have sound. And there's one more. Light, sound, force, and heat. Okay. These are very nice. All these things are very nice. These are good. So this is a way to observe electricity. But the one that really is important from the point of view of understanding all this is through the force. So magnetism will be something similar, right? It will be, what is magnetism? Magnetism is going to be the interaction of what will we call this? Interaction of magnetized oh, I need to charge this thing. Is charging, right? Of magnetized bodies or moving charges. No, you so reduce the volume there. Okay. Now I have a asked ChatGPT, what do you think electricity is? And this is what it gives me. What is electricity? That was my question. And ChatGPT is telling me it's a form of energy that results from the movement of charges of particles like electrons and so forth. So ChatGPT is not being very precise. ChatGPT is saying that it is the movement. But we all know from our basic experiments in high school that charges, static charges, interact with each other. They don't need to move, but you feel the force. So ChatGPT doesn't give you a professional definition of electricity. Then I went and said, well, let's see, if we're talking about definitions, for sure, Merriam-Webster should have a good definition, right? And this is what Merriam-Webster says. It says it's a fundamental form of energy, observable in positive and negative forms that occurs naturally as in lighting or produced as in a generator and expressed in terms of movement and interaction of electrons. Much better, yes.
Someone's saying that they only can see the cloud that you put as background, but
I see. Okay, let me see. What is what I am sharing? Okay. What is what you see?
Here.
So what they need to do in Zoom is that they need to themselves, whoever is doing it, you need to look for a way where you don't see the participants. You need to see that you say the share material. So it's on your side.
Yeah.
A suggestion here is that you minimize the participants and you will be able to see it. Everybody else is seeing the right screen. So I think it's on your side. Let me see what is the chat.
thanks.
Sixto is okay now?
Yeah, we can see the presentation.
I don't know. Carlos, pregúntales. Okay. ¿No? ¿Te
Yeah,
contestó?
sorry.
Okay. All right. So I like a lot more Merriam-Webster. Merriam-Webster definition is pretty good. It starts with something that is a fundamental form of energy. So it's energy. Energy is exactly money. Force is related to money, but energy is money. There is no way that you're going to have energy with you don't pay. So it's a fundamental form of energy. Fine. And it's observable. That doesn't matter. But what is important is that it is the movement and interaction of electrons and other particular charge particulars or charge particles. Okay. Other things that could be electricity, people normally call electricity the fact that you have power. So if you have at your home, you have power, you say, oh, I have electricity. So electricity can also be a human interaction when you see, oh, that person is electric, right? But that's not what we want. We want the physical meaning of electricity. Okay, so anyway, I'm looking at it, it has to do with force. Okay, so force, energy. Energy is going to be in the most, let's say, basic way, it would be force product of distance. And what he's saying is, let's say that you have a force, and for now, this is wind. And you are here, there is a person here walking there, right? It's you are walking over there against the wind. You need to put some force in there, right? Force times distance is how much energy. We will see energy will be force times distance. And this energy becomes directly money. The example I always say is I ask a student to take a chair out of the room one time. And the students, well, they do it correctly. They do it because they think, oh, this guy with the ponytail is kind of crazy. Let's listen to him. But if I tell you to do it 10 times, you would start saying, well, what is this? You need to pay me. So if I give you $100, you take the chair out. So if you're going to spend some energy, somebody needs to pay for that energy. So why is this person trying to go this way? I don't know. Maybe there is a food over there, or maybe there is some other motivator. Other motivators may be love, maybe more money, maybe who knows, right? But somehow this person decided to spend some money and walk against the wind because something on that side is something that he or she likes. Okay, so in the most fundamental way, this is the equation. But we learned how to take integrals over a. Let me get to the integral as a conclusion. Say now that the straight path, the force is still here, but the straight path now is not straight. Now you go this way a little bit, you go that way, then you go that way a little bit, and you go a little bit less, more, less, and you are walking. This is still the same walking person. It could also be a car. It could be, who knows, anything that you're pushing, and you're going against the wind. But now, the equation is not straight. This is fine. This is tell me if I spend the energy going exactly in the opposite direction of the wind. So, but if I am not going exactly in the opposite direction of the wind, there is a component of that. So that I need to somehow get to the component that is in the direction of the wind. Of course, here will be the cosine of the angle or whatever. But I have several paths, several things. So it comes to give me this equation now becomes, and there will be a negative sign. There will be a negative sign because I am going against the wind, right? So now the force here will be, or it will be the integral over some path, which I'm going to put a C for the English word of contour. Force as a vector, distance as a vector, or dl as a vector. So now it is, we have made it an integral and we have established it as a vector. Now, what is really a vector? So, and of course, remember, this is equals to the money that you have to spend. Let's say now that you go against, you don't go against the wind, but you go towards the wind. Now the wind is doing the work for you. You don't need, you just need to let it go and then move it. It's like if you were going up the hill or down the hill, the same thing. You go up the hill, you have to do work. But if you go down the hill, the mountain is doing work on you. So what? Gravity, right? So if you are getting paid for bringing, I don't know, some peanuts from point A to point B, and the point B is below you, they are paying you for almost no effort. But if you have to bring them up, now they are paying you for your effort. When you get up the hill, you're going to be sweating or at least tired. But if you go down the hill, you will not be tired. So, but you're getting paid for the peanuts. So, all right. So force, I am here some way saying these are vectors. We all know what vectors are, right? It's just a representation of forces. So, and the best representation or the most common representation is to say in the field. What is the field? I am not talking about electric field. I am not talking magnetic field, force field. I'm just talking about a physical field. What is a field?
2 points from A to B, or any distance from point A to point B.
I think it's more than that. Field includes that. But a field is, first of all, it's a space. It's a physical space. We're talking about something that is physical and exists. It's a space, but it could be one-dimensional, two-dimensional, or three-dimensional. Of course, humans will live in a three-dimensional field. Now, many times when we're going to talk about electromagnetic fields, we're going to do simplifications to 2D or to 1D out of the 3D, but reality is 3D. But sometimes there is a geometrical I must say characteristics that tells you what is the point of doing a 3D when a 2D is enough. And some other times you say, oh, 1D is enough because it's a whatever symmetries or physical characteristics of the phenomenon and the materials involved and the bodies involved allow you for such a simplification. By the way, in finite elements, we don't need to do any simplification if we don't want to. We can model things exactly the way they are. Not many times it's not the smartest way to go. In many ways it's better to do 2D, and many ways is to do some sort of symmetry things, depending on the size of the model. Some computers, many computers may not be capable of modeling a big, large power transformer of 300 MVA. Probably they will not be. At least your laptops will not be. You may need a supercomputer or something to do it. Okay, but field is a space. But the field that we are interested, it's a space where we feel where we can measure force, either electric force or magnetic. So those are the two things that we care the most at this point. Those are the only two forces that we have based on electromagnetics, which is electric on magnetic. And if we cannot measure force, we can say there is no field in there. So a different thing is don't confuse the field with, for example, the vector E, right? Which we normally call the electric field intensity. Okay, here, this quantity E or this vector E is already measuring something. Yeah. So it's measuring the intensity of that force. So and if you remember, this would be the force divided by the charge. So as you can see, it's directly related to force. And the moment you have force and you move, you either gain energy or lose energy. And therefore you make money or you lose money. That is a one-to-one relationship between movement against or with the force. So I think I have a vector field here. Yeah. So these are some of the fields that we are used to. So we are used to having electric field, which is given by force, is related by force by the charge. The magnetic field is also given by some force. I mean, the magnetic forces are much stronger than the electric forces. If you bring two permanent magnets, they will attract or repel much faster than the or much stronger than electric fields. Okay, now there are other things that are important. Magnetic flux. So we can still see some physical thing into the electric field and magnetic field. They are related to force. But have you ever seen magnetic flux, electric flux, or electric current? We don't see them. We just believe they are in there. We see their effects. These things are not visible. They are not visible. They are how can I say, models. You can say these are models that that help us understand. Not only understand and compute things, right? And use them. Understand and use these forces. So magnetic flux is telling you that there is already some quantity of something going on. Flux Flux is related to quantity. So it's the amount of something that is happening there. Electric current is also a measure of quantity. I mean, you can actually say you can count how many electrons are passing. So you say, I don't know, 1,000,000 electrons are passing here, right? And therefore, I have such measurement of current. The measurement units and the measurement system for all this was invented late in the 1800s, 1860s, somewhere like this. 1860s is when the some measurement units were starting to pop up in electricity. I think established correctly was probably only in after 1900. So and even then there were some different the CGS and the NKS and many other measurement systems. Today we use the SI in the entire world, the international system, and except in the US, which we don't use international system for many things. We still use inches and feet and yards and miles. So, anyways, so these are quantities, right? These are quantities. These things are related to force. Yeah. Oh no, not it's related to force, but in space. Now, everything else we're going to do is mathematical models. At to this point, we kind of somehow think everything here is physical. So yes, we even though we cannot see the magnetic flux of the electric current, we can certainly see the effects of electric current. The minimum thing, the most basic thing you will see from electric current is heat. So if you put electric current into a conductor, it will get hot. And you can also do an experiment if you think that it doesn't exist, the electric current. Grab 2 electrodes and electrocute yourself, right? And you will see. Now you will feel it. Now you will certainly feel it. But if you don't want to go that aggressive, you can simply see that a conductor that is carrying current, even though you don't see the conductor is getting hot. All right. So up to this point, we are talking about physics. These things kind of exist. See, electric field exists, of course, there is a space. And in that space, I feel forces, then I have an electric field. Electric forces, I have an electric field. So far, there is no math here. It's only physics. Now, there is a next concept, which is the vector field. Now, this is a mathematical abstraction of a physically observable of physical observable phenomena. What is this physical observable phenomena? Of course, the force. That is what we have, is the force. And we know that if I have a charged particle, a charged sphere, for example, here I have Q plus, we already know that the electric field is, say it's a metal, if this is a metal, is perpendicular to the surface everywhere. How do we know that? Well, yes, you kind of want to talk. Or you don't want to talk? No. Okay, so how do we know that the forces out of a sphere are radial to that sphere? Let's say it's a metallic sphere. How do we know?
Because of the direction of the electric field. That should be normal to the surface, I think.
Because we have reaccommodation of charges. So I don't know if you guys at any point in your high school or in your undergraduate or somewhere did an experiment when you had two charges. You had a positive charge and you have a negative charge. And the negative charge is assumed to be the forces to go into there. I don't know if you did an experiment with pieces of paper and you got a little piece of paper and put it here, and it was aligned and aligned and aligned, and you could put another little piece of paper and it was like this, like this, like this, and so forth, right? And it also coming here, you could see pieces of paper. So kind of, and if you haven't done it, it would be great that you do it. I mean, all these professors then in Mexico, you have a better labs than us. So go to your labs and create. I don't know if the electrotechnics lab still exists over there, but I remember seeing this experiment there. I did it in there in the big lab in the Pesados 2. Oh, that was great. This electrotechnic lab over there. So do this experiment, and you can see now that the force is transmitted one side to another. Now, this tells you that there is some force in there that that can be described mathematically with something called a vector field. So those lines that we're putting there, those are abstractions of something that we can observe. We can observe the force. We can observe that these things align. The same if you have two magnets, right? You say to have two magnets, north and south. And then here you will have also the south and north. And you will have these lines here, and you will have some fringing over here, some fringing over there. And you can also see these other things, right? You can also see the fields coming from here, coming to the other side, like that. And now this is even more visible because you can have iron shavings, little iron shavings with ink, right? And they align very nicely. And actually, they can even give you a print of what this is happening. So, so it means that there are that we can somehow say there are vectors here, right? Because they have to be aligned with the force. We are feeling the force between these two things. There is an attraction force. The force is here. So, and the force seems to follow the path of these little things. So, a vector field, even though it's a mathematical abstraction, it gives us with some physical easiness. So we say we can feel comfortable representing these fields with a vector. And we come to put a vector, the force vector, and we have to select some coordinate system. We always select X, Y, Z, and even time. So, and this is what is a vector field. A vector field. So it's a function that it may have several directions. Yeah, it is a function of X, Y, Z, and T. And if you were to go even more, a bit farther, being this a vector, it will have a component in the X component, which is a function of X, Y, Z, and T in the X direction. plus a component in the x, y, z, t in the y direction plus a component in the z direction of x, y, z, and t, and unitary vectors. These things are unitary vectors, right? Which means it's just the direction in which this is applied. These things are unitary vectors that give you the direction, basically the direction. In most final elements things, even if you have cylindrical symmetry or spherical symmetry, we still program things in the XYZ. So I am not going to go into cylindrical coordinates, spherical coordinates on any of those crazy things, because in my view, they only obscure what we want to know. What we want to know is where is this force going and where is this force is coming. And is the force, you can call it electric field, magnetic field, flux density, you can call it by any name. But what it really is a representation of the force. So when we say it's a vector field, it is the force. And if we move, it is the energy, which is the money. Okay. All right. So let us be very clear. This vector field doesn't exist in the physical world. It exists if we are able to measure it, but we measure it indirectly. We measure it through the force. Can you actually measure magnetic flux? How do we measure magnetic flux? We put a coil and we say what is inside there. Normally we induce some field and then you use formulas. So we use formulas to measure. So that means that is not a one-to-one representation of what I am measuring. But the only thing really that we can measure is the force. Yeah. And if you measure force, and to the point, let's say that you go far away, you have this is a positive, you have an electron here, and you move it far and far away. The field ends when you cannot measure any force. If you cannot measure any force, maybe your measuring device is not sensitive enough. But if you cannot measure it with anything, you can simply assume there is no field there. Or the field is sufficiently far that it doesn't matter. Yeah. For my people here, I have already said it many times in the different courses, but I will say it for the Mexicans. What is the appropriate engineering error that you can take? How much is engineeringly speaking valid to take a to be the error? Basically, what I want to say, how small this needs to be so that I accept that it is zero. And if you guys want to unmute and talk or ask on the chat, please go ahead. And I don't want to put anybody on on display, but is there an answer, Carlos? Nothing.
When the effect is maybe
Engineering error.
engineering.
Somebody's talking. Fermin?
Yeah, well, I was
think you're muted.
thinking that this, maybe when the the quantities cannot affect, I mean, we will not have an effect in what we are measuring, what we are seeing.
If you can, yes, you're right. If you cannot detect it, it doesn't really
They're
matter.
gonna detect.
But you know it's there. But you know it's there.
Mhm.
But I want to say, even doesn't matter. You can still detect it, and it doesn't matter anymore. Or basically, or the other way is how sensitive your device need to be so that you can measure what you need useful. So basically, what percent error what percent error is acceptable from the point of view of an engineer?
5%.
5%. Anybody gives me more or less? Fayaz gives me here 10%. Hey, let's. Hey, we are full of engineers. I mean, everybody in this room is an engineer. I will believe that everybody on Zoom is an engineer too. So let's make a decision. So, and the way Fermin put it is right. It's when it doesn't matter. So I am going to talk in U.S. terms because I don't even know how much is the conversion of a peso today. But what is a good salary in Mexico, Carlos?
Like,
A good salary for an engineer.
35, 40.
25,000 Mexican pesos per month.
Per month.
Convert it to the dollar so that we have the same.
The
Well,
they can talk dollars, right?
Yes.
So 35,000 is probably like $2,000 a month. $2,000. So $2,000 a month, and it would be 20. I'm gonna make it at 25,000 per year. Okay. And you guys don't laugh about the salaries.
We have much lesser than
It's
this.
1,000.
But
We
that,
have much lesser than this.
yeah, all right. So anyways, say how much error I am willing to take. And say if they offer you a job that pays you 24,000, is it okay? Would you accept it? For the year, so which be let's do it with the 2,000 is best. 2,000 a month. So would you take 10% error, which means 1,800 a month? Would you accept 10%?
Maybe yes, maybe no.
Maybe yes, maybe no. Exactly, depending on what? Depending on other things, right? But if they offer you 5%, say now they offer you 1,900 pesos a month. I think it would be fine, right? It could be fine, maybe not. But if we go to 1%, which means now they're going to offer you 1,990, right? Would you consider this equals to 2,000? Would those 10 pesos really matter anything to you?
No.
Maybe 20, right? Maybe this is an 80. So 1%, it's already too much, right? I mean, nobody will say, no, I'm not going to take it because it's 1% less. Maybe some people would take it at 5%. I would say if the alternative is to be unemployed, we will all take it, right? But if they offer you half, so 50% error, if they offer you instead of 2,000, only 1,000, you may say, I may wait for the next job, right? So the same attitude we take towards how much this zero needs to be close to zero. So at the point that it doesn't affect you humanly speaking, which is 1%, 5%, between that range, it doesn't affect you from the point of view of humanity, then that's an engineering error that is fine. 10%, maybe yes, maybe not. And that's the perfect answer because it depends on, first of all, what else is there? And second is, what is the actual effect of this 10%? If this 10% is so much, say, this 1,800 is enough that you cannot pay your rent, well, then you will not take it, right? Unless you're forced to, but you will keep on looking for another job that pays you better. So, all right. So we don't have to do things in engineering exactly. And this is the way I am going to teach this course. I am not going to go through rigorous mathematics, but I'm going to go through approximations that work. Because final elements, that's exactly what it is. It's an approximation that works. It doesn't solve the problem accurately. It doesn't get you to the 100% accuracy, but it gives you a workable solution, something that engineers are happy having. Okay? All right. So if there are questions, please interrupt me here in the room or online. Okay, I always like to discuss the properties of magnetic materials because we know we have magnetic forces, electric fields, magnetic fields. Oh, I put the fields over here, right? So not yet. It will go down. But these magnetic and electric forces play a game in the field, and that field has properties. So, and is magnetic properties of electromagnetic materials in the field. Basically, in the field, we play games, we play sports. Maybe we are in the field. Maybe some of you like football, soccer. Some others like American football. Others like tennis. Others like whatever. Others don't like any sports, but still know them, right? Cricket. Oh, here we have 3 Pakistanis that will be. Cricket is the sport. Maybe you still like cricket? Not much. Not much. All right.
Only
Yeah.
only 2 or 3% is playing, and all of the rest standings.
Yeah. But you like cricket?
I do like
You don't, you like it? No? Oh, come
I
on. You
don't
like
think it
cricket?
is a sport.
No? No, I don't even understand it. But anyways, there is a field. We are going to play the game of forces, magnetic forces versus electric forces, or together. But there is a some rules. And here, the electromagnetic properties of these materials are the rules, right? So, and even though you already know it, I want to keep it here because it gives me the opportunity to explain things of why things are done this way. So, for example, conductivity. Conductivity is represented by sigma and is given in Siemens meter, which is, of course, ohms negative to the -1 by meter. And this property divides all materials on Earth into superconductors, conductors, semiconductors, and insulators. A superconductor has a conductivity of infinity, and that's it. Infinity, and it doesn't change. Conductors have a conductivity approximately 10 to the 7. Copper, for example, is 6 or 5.8, 10 to the 7 for copper. This will be for copper. Aluminum is probably a little bit less. It's probably 4 or 3. Let me change it here. So copper will be about 6 point something, 6.7 or 6, 10 to the 7. Aluminum is 3, 10 to the 7. And these numbers are just what I can remember. Semiconductors have something in the order of 10 to the -4 to 10 to the 4. And insulators, the good insulators used in electrotechnical devices, it will be 10 to the -14. And here is where we have the great success of electrical power engineering. Why is that we can transmit power? Is because the insulators versus the conductors have 10 to the 21 orders of magnitude difference. So that allows me to put a very thin, very long conductor wire with a very thin insulation layer on top. And if I impress current here, the current will come out here much better than leaking out into the outside of the insulation. So I have made a calculation, and if you have a conductor diameter, a copper conductor diameter of 1 millimeter, copper diameter of 1 centimeter. If you have 1 centimeter of copper and you have PVC insulator with 1 centimeter thickness, the length in which electricity will prefer to go through the conductor rather than leaking outside is 547,000 kilometers. And I will put this thing in there. So 547,000 kilometers is more than going to the moon. It's about 20 times, it's 40 kilometers going around the Earth. So it is like 15 times, 40, no, not quite. 14, 13 times around the Earth in the equator. So if you put a conductor all around the equator 14 times, which of course is physically impossible, electricity will still prefer to go through the conductor rather than jumping the insulator. Hey, with such a thing, we electrical engineers have no way to lose. We're already winning because these properties are very good. Okay, so so these are the games. We're going to play the conductivity game. We're going to play sometimes when we have electric current, we're going to go through the conductivity, and we are going to assume that insulation is just perfect insulation. We cannot build anything this long. 447,000 kilometers is not possible. The second property that I like to deal is mu, which is the permittivity. Permeability. Permeability is represented by letter mu, which is always given by mu 0 times mu r, and this is given in henries by meter. And that divides the materials in ferromagnetic, ferrimagnetic, paramagnetic, and diamagnetic. Relative permeability of a ferromagnetic material mu r useful in engineering is somewhere between 2,000, maybe if you have something good, 3,000. Of course, you can have experimental or very expensive, very fancy materials that can have up to 10,000, easily 15,000. But we don't have the money to pay for them anyways. So ferrimagnetic materials are much less, are probably between 500, and they are making them better and better and better. They are approximating, I would say, 1,500. But they are making them better, and they are also making better the saturation point. So ferrimagnetic materials are going to, I think, probably be very good. Paramagnetic materials, mu r is approximately equals to 1, but mu r is greater than 1. And diamagnetic materials is approximately 1, but mu r smaller than 1, not than 0. All of those are, the ferromagnetic materials are all conductors because they are basically, there's 3: iron, cobalt, and I'm missing one. And nickel. Yeah, those are the only ones. Thank you, Carlos. So it's iron, cobalt, and nickel, and combinations of them, alloys of them. So they combine and they give you different things. Now, the good thing, so these are all conductors, so they have high conductivity. Now, the ferromagnetic materials are insulators, so they are very good because ferromagnetic material that you can use in a machine for alternating current is going to induce currents, eddy currents in the reverse thing, and you're going to be wasting material. Ferromagnetic materials, they will not induce any eddy currents, and you will have the full power, except that the power is still, or the, let me say it this way. How do I see? I see conductivity as easy between where is easy to go versus where is not easy to go for the current. The way I see permeability, this is the magnification factor of flux density. Very simple. How do we see this? I have a magnetic core, and I have a, and I need to make it a bit larger. I'm going to have a magnetic core of a transformer. This is a transformer, right? And it's a transformer that used to give classes because the transformers are never built this way. But you have the primary there, you have the secondary there, right? And because you want to induce voltage over here, voltage of the secondary, you apply voltage on the primary, alternating current, and then the flux is all apparently all concentrated here, or most is concentrated. That would be the linkage flux. If you have linkage flux, it will go in the middle. But still, if the if this has a permeability, relative permeability of 2000, and this is air with a relative permeability of 1, the probability that the flux goes in the core is much higher than if it goes around. It goes out. But also, this allows me to induce voltage, right? I want to induce voltage given by the frequency. So omega mu it minus d phi dt is going to be omega magnetic flux density times area. Magnetic flux density, I am entering into things that I don't want to discuss now. But what I'm saying is if your permeability, omega mu HA, if your permeability here is higher between mu zero or say mu r equals to 1 or mu r equals to 2000, what it means is that if you have, for example, a number of turns here and number of turns here, it means that the number of turns can be 2,000 times smaller for the same voltage induced. That makes the device a lot smaller. So an air core transformer will be humongous. So this permeability, relative permeability, I see it as a magnification factor. So how many more times I can induce voltage in iron than in air? That's what permeability means. I mean, if any one of you has ever built a transformer, you will see that you don't want air gaps. Those air gaps, you'd really pay for them very expensively. Okay. The last property I want to see is permeability. Permittivity. Not everybody is sleeping. Permittivity. Permittivity. I don't like it. Permittivity. And that divides the materials in only two. Dielectric and non-dielectric. Permittivity is epsilon, which is given by epsilon zero times epsilon r. Of course, mu zero here is 4 pi 10 to the negative 7. And over here, epsilon zero is 8.85 10 to the negative 12. And a something I'm missing here. No. All right. Now, dielectric materials have a relative permeability typically between 2 and 6. And non-dielectric materials have epsilon r in the order of 1, which means that I cannot do a lot of magnification here. I can do something, but 5 or 6 times. Not in here, I can do 2,000 times for a magnetic field, and for conductivity, I can do 10 to the 21. So it's, of course, this is used to build the units here, farads by meter. Of course, this is to build capacitors, this is to build inductors. So to store energy, it will be probably better to do it in magnetic materials, except that magnetic materials don't hold the property. So so those are the rules of the game. Whether you have some electric fields or magnetic fields, they need to play whatever is the material. If we have only air, well, you will use all the properties of air. So any question to this point? I know it's been very elementary, but that's the way I want to take it. I am going to go slowly incrementing things. Here, I'm going to start with the electric and magnetic laws. So what are they? Ohm's law. What is Ohm's law? Let me see, what is this? Experiments here. No, I think this is time for me to start. Before I get to that, I am going to describe the vector fields. The vector fields that we're going to use. We're going to use electric field intensity, which is given by Newton's meter. No, Newton Coulomb. Yeah. J is electric current density. Which is going to give amperes by meter square. Then I'm going to have D, which is an obscure vector, an obscure quantity, which is electric flux density. And it is obscure, and this is given in coulombs by meter squared. And it is obscure because we are very much used to V, magnetic flux density. Which is given in Teslas. It's given in Teslas. Teslas are Webers by meter square, but now we use only Teslas. So the magnetic flux density is very clear. We all understand it. We draw it. We come to this transformer, and nobody asked any question. I just drew the flux, and we are all happy. Yeah, but electric field, the electric flux density is a little bit more obscure. It's the field that happens inside the capacitor. So you have a capacitor which is fed by an alternating current. We know that we have here an insulator. If we put here an insulator, which also is a dielectric, and please note that it's not the same that something is dielectric, that something is an insulator. An insulator has to do with the conductivity, and a dielectric has to do with the permittivity. The permittivity, if you want to think this way, is the capacity to form dipoles.
Dielectric can be insulated or,
All dielectric are insulators,
okay.
okay?
And all the.
Not all insulators are dielectric, okay? So the capacity of forming dipoles. What is what I mean? That if you have an electric field or a voltage applied between a dielectric material, this material will give you dipoles. It will separate the charges in the molecules if you want, but don't break them apart. They are not breaking, they just separated in the molecule. So that's what a dielectric can do. Okay, but that is the property of a dielectric. So that's why they can store energy, because they separate, and provided that you don't change, don't reverse the excitation, the charges remain. Okay, so the other property there is H, which is the magnetic field intensity. That is given in Henry's meter. No. Ampere meter. Ampere meter. Yeah. What's that?
Electric current density and the magnetic field intensity, they have the same unit except the square.
Exactly. Yeah, they are cousins. Very, very close cousins. You only need to take a derivative of one to get the other, or the integral of one to get the other. Space integral. Very good observation. Yes, they are very, very close.
So just like a traveling charge, we can be acting over. It can create a magnetic field and electric field simultaneously.
Correct. A traveling charge creates both simultaneously. Normally in opposite directions, or in different directions. The traveling charge creates an electric field in the direction of the travel, and a magnetic field in perpendicular to the travel.
They are quadratic.
They are in quadrature, if you want to think that way, mathematically. Yeah. Yeah. Is the space derivative or the space integral. Space derivative, just like in time derivatives, they shift 90 degrees.
Yes.
Okay.
Yes.
Yeah.
If you take a
So it's the same thing. Yeah, if you know how to take those derivatives on your frequency domain functions and shift, the same happens here. Okay. All right. Okay. Electric and magnetic laws. So now I know the vectors that are playing their game. So we could start with Coulomb's law. This is the simplest one. Coulomb's law establishes what? That the force is given by a constant, Q1, Q2 by the space square. So what is what Coulomb did to get this equation? Experiments. So this is an experimental load. It cannot be derived from basic anything else. This is just an experiment.
like, like currents and voltages, they are also related by some derivatives. Like if we see inductor, so what we see, the voltage is equal to LdI by dt. So they are basically, if can we have a same analogy with the current and voltages as we have the same analogy with this intensity and the
It's the same thing. It's the same. It's the same equation.
same.
It's the same equation. Maxwell equations are those things. Maxwell equations with some simplifications become the circuit equations.
Okay.
Yeah.
So which one is derived from this one? Which one is derived earlier?
No, none of it is derived. Everything is observed. Okay. There is no derivation on electromagnetic laws. It's only experimentation. Okay. From experiments, you write an equation. You observe what is happening, and that you put an equation. But there is no derivation from some other basic concepts. Yeah. You're taking his way. Oh, he's there? Okay. Okay. All right. So Coulomb's law, we know. Who doesn't know Ohm's law? What is Ohm's law? What? No.
Provided that resistance is kept constant.
But no, but when we are talking vector fields. So in a vector field, Ohm's law tells you that the current density is equals to the conductivity times the magnetic field intensity, right? Those are the vectors, right? Those are the vectors, and so electric current density J placed together with the electric field intensity. And let's see what these things are. Electric field intensity is force divided by charge. So E is a force, and J is a product of the force. It's the current. How much current is being pushed? Well, you have to put a force, and you need to tell me how easy or difficult it is for those electrons or charges to move through the material that you have, right? It may be that the conductivity is infinity, and it doesn't matter how much force you put, there will be no current. It could be that it's a good conductor, and then you only need a little push, a little force to push the electrons from one side to the other. So you have an electron here. If this is a high conductivity material, the current will flow easily. But if it is a high or a low conductivity material, like the one we would put around here, then it is very difficult for the current to come this way. Okay, so that is Ohm. What is the experiment that Ohm did? Now, bear in mind that I am talking about these vectors, and all of these vectors, in particular, let's say J and E, are a function of X, Y, Z, T, and they can have three components. They have the component X, the component Y, and the component Z. So it's an entire vector field in 3D, right? So, and this Ohm's law exists there. I am going to get into open, insert a page above. So we have Coulomb's law, Ohm's law. What is the next one? Easy. What? Faraday, no? Kirchhoff? The Kirchhoff is more advanced. Kirchhoff is later. Yes, Kirchhoff is good, but it's later. Faraday's law or Ampere's law. Which one you want? You. Which one you want first? Ampere's law. Ampere's law. What is what Ampere's law tells you? In words, just in words, is telling you that the magnetic field is equals to the current enclosed. Magnetic field around the path is equals to the current enclosed. Mathematically, this typically we have said that it is the closed integral of H dot dl equals to the current enclosed. And this is nothing different than if I have a conductor here, it's carrying current here, I can imagine a magnetic field that it is around here, right? Circles and circles and circles here and circles here. And I have then a question. If I look at it from this point of view, and the current is coming out the paper, and I know I have a magnetic flux, I have a magnetic here, H here. This is, of course, the current. The inner part is the current, right? So, and the blue part is the conductor. And I know I have magnetic flux outside. The question is, do I have magnetic flux inside the conductor or not? What do you think, Rizzo?
You should have it.
You should have it. Why?
It's if you divide the conductor into several like sections.
If I put an Ampere's integral around here, right?
Yeah.
It will still enclose some current.
Yes.
Yeah. So there is field inside. Only in the very center there is no field, right? Who knows? Because that is a singularity. And then singularity, who knows what happens? But we don't care. Remember, we are not doing things mathematically accurate. What we want is general engineering understanding. All right, so that's Ampere's law. Perhaps before Ampere's law, we should have put Gauss' law. Gauss's law. Gauss' law is telling you the same. Now, it's if you have a body that is charged and you have a surface or a closed surface, it will tell you the integral of the flux coming out is equals to the charge enclosed. Okay, so here is the relationship, very clear relationship between the charge and the flux and the electric flux density. They are just related by the area. If everything is constant, like here, right? The flux is coming out like this, like that. Okay. If the flux is just coming out this way, then you can simply say that D is equals or D times area is equals to the charge. So forget about the integral of those things. You just say what is the area that is enclosing this, assuming that it's uniformly distributed, which it will be for now. And that is equals to the charge. So you can measure the charge by integrating a volume, and it doesn't really matter if that volume is close to the charge or it is a meter or 100 meters away, provided that you can still feel it, right? Okay, so where are the game of things? All right. So that's Ohm's law, and that will take you to Gauss' law, and you can establish that also a rule between D and E, right? So how much flux is coming out? Well, it depends, just like before, just like we did with Ohm's law, right? Depending also on the material's properties. So the E is the excitation, normally, electric field is the force. D is the amount of flux that is coming out, and it depends on the permittivity. How high or small, high or low is the permittivity, is the amount of flux that you can get. If there's a material that doesn't allow, let's say it has a very low permittivity, how low it could be? 8.85, 10 to the minus 12, which is pretty bad. This is epsilon zero. Okay. So that tells you, well, the electric flux density is kind of small. Yeah. What is the last one? The last one will be Faraday's law. Faraday's law. Tell me, what is Faraday's law? Integral of E dot dl equals minus
Partial of P over.
d dt of flux, right? Which we can say is d dt of VA, right? No, this is the other way around. This is d dt of B. Yeah. No. This is the voltage. No, okay, this is the voltage. This is the voltage, and it is d dt of flux. Right? That's okay. That's correct. The negative. This is correct. Okay, so this is Faraday's law. Important thing is this relationship between the voltage and the electric field intensity, and the voltage. And also important is to know that variations in the flux with time is what induces the voltage. Okay. Now, from where do we get all these things, all these formulas? All of them are derived from the experiments. Kashif is gone, but I would give an example for him in a moment. If he comes back, I'll do it. Okay, so these are derived from experiments. They cannot be derived mathematically from any more fundamental things. They are from experiments. So I would ask you, everybody in here and online, to design experiments. We are all here. The people in Mexico, they are all professors. So, and here we have, except you two, PhD students. But you are already engineers. You have made money out of engineering already. Have you? Yes, right? You have made a lot of money out of engineering. So, design an experiment that will demonstrate demonstrate the validity or not validity of any of these laws. So, what would you do? How would you say this would be K1, K2 by R squared? Well, you charge two loads, right? Place them together, do two charges, you charge two bodies and you get it together. So then Ohm's law will be very easy, right? You would say voltage equals to resistance times current, right? And you come and build a circuit and you see that you will see that this is actually instantaneous too. Voltage resistance times squared. And it also works non-linearly. So voltage of time will be resistance as a function of voltage as a function of time, current of time. So if the resistance changes with time, or if the resistance changes with voltage, no problem. The law is still the law. And this is what we're going to do. And it's even more general. This is even more general than that. It could be a function of space. So the voltage could be a function of X, Y, Z, and T. And the resistance will be a function of X, Y, Z, T, and a voltage, which is also a voltage, which is function of X, Y, Z, and T. And it will be also multiplied by the current, which is a function of X, Y, Z, and T. So, and this is written when we go to the point by point, it's going to be written as electric field equals to 1 by conductivity times current, which gives rise to J, which is going to give me that J is equal to sigma E. But sigma can be a function of many things. In particular, sigma could be given as a matrix. Then it can have sigma XX, sigma XY, sigma XZ, sigma YX, sigma YY, and so forth. You get it. So this we'll call it a tensor. We call this a tensor. So, which means we need to specify if the media is isotropic, homogeneous, and linear, or anisotropic, non-homogeneous, anisotropic, non-homogeneous, and non-linear. So, what? So, it is impossible to do these calculations by hand. When you start having a general things, real things, machines, real installations, we cannot even solve this thing easily because it could be nonlinear. Each one of these can only be It could depend on the direction, but it can also depend on the function. It could be a function of voltage, for example, or a function of current. So things get complicated, but let's not complicate our lives now. Propose an experiment that validates Ohm's law. What would you do, Rizzo? What would you do? You want to become a professor, right? Or you can change your path.
Got a little bit,
Sleepy. Okay. Should we take a break? No. Should we take a break? No. You are okay? You are okay? Okay. All right. So design an experiment. Anybody, can you design an experiment to and I make it easy for you. Just get a circuit, right? Get a circuit, voltage, a resistance, and measure the current here, right? Voltage. And it could even be a DC. It could even be a DC voltage, so plus and minus. So you take a resistance, you will plot this. This will give you the resistance. If this is the voltage and this is the current equals to resistance times voltage, you should get a linear thing in there, like a line, if the resistance is not changing. Nobody's telling you the resistance cannot change. The resistor can change, right? This resistor can change, but let's do a circle like this. Is this enough? For me, this would not be enough because it's only one experiment. It's only one line. But what if I change the value of the resistor and obtain different lines? What if I change the value of the voltage? Instead of being DC, now I make it AC. And then, of course, I need to get a time domain function. This is time, this would be voltage and current. And the voltage I apply is like this. And the current will give me something the same shape, like that, because it's linear. But if the voltage I put now is something crazy, for example, let my voltage disappear here and it starts immediately high, stays constant, then it drops down, and then it goes like that, right? And I put it like this, because this is my class, and I put the example I want in my class. So if you have a linear resistor, what would be the current? The current will be proportional. Say that the resistor is less than 1. It will be higher, and it will be like this, and will follow that, and will follow that, and will follow that, and that will be the current. The thing is that the voltage with the current will always be proportional to the voltage, and this proportional is called 1 by resistance if it is linear. So it doesn't matter if it changes with time, if it does whatever, the current will, on a linear resistor, will be an image of the voltage. Okay. So I am not going to go through all the experiments, but think about experiments that would validate, as we will say here, beyond a reasonable doubt, validate a given law. So for all of them, there is going to be an experiment or a set of experiments that will validate all these things. Today, we are at a point where we just believe the equation's right because there hasn't been really an experiment, and let me change a little bit that, a macroscopic experiment that says that Maxwell equations are wrong. There hasn't been such an experiment yet. If you go to the soft atomic particles, yes, there are cases in which kinds of doesn't fulfill right. But that happens only at the microscopic level. In the macroscopic level, in the world we live, there is no experiment yet that tells me that Maxwell equations are wrong or not valid for certain things. So if we want to solve electromagnetic problems, Maxwell equations are the way to do. We have to solve Maxwell equations. Now, Maxwell equations is a set of equations that look ugly just looking at them. Yeah, I have them here. So these are Maxwell equations. You've probably seen it many times, but they are absolutely ugly and they are very difficult to explain to students on second or third year undergraduate. They are very difficult to explain to graduate students who have taken them already before. Okay, but these are experiments. Now, what we do, Maxwell put them together. Maxwell's contribution really was only this part, in addition to putting them together. So he put them together. Ampere's law existed before, Faraday's law too. The continuity law also existed before. Gauss's law, of course, existed before. All these other things existed before. I can give you a right space access. Yeah. So you just need to send me an email because I didn't know you were going to come. You are not also in the, you want to be up, given up. And you, I think I put you in the right space. I'm using Rizzo's class.
Oh.
You are the only one registered for this class. Everybody else is just not registered, but are there. Did I put you?
Everybody, because he has also dissertation credits with this course.
No, but I use one of the bright space. I use Rizzo's bright space.
Yeah, I can say.
Log in with your own Zoom.
I created a bright space for Rizzo's course, and in there I'm putting the material. And if you didn't receive an email saying,
I received an email.
okay,
The
then
BK09 is the dissertation room.
it's Rizzo's space.
Okay.
It doesn't matter. You have the link, you get in there, it's in there, it's active for you. The material is there. You've downloaded the material or you've seen it already, at least. Okay, so somebody, I don't know if Rizzo or Carlos, should actually, Carlos, I think is not gonna come to too many sessions because Carlos has seen it already many times. So it's, how many times can you see the same movie? Yeah. I don't know. How many times can you see the same movie? 5 times.
9.
Yeah.
Depends how much. Yes. If it is very interesting and it gives you some, it takes you.
So you see,
in other words,
so Carlos is here. Carlos is here just to be entertained, not to learn. Okay.
every time he could have other perspectives.
And Fermin over there, he has taught this class many times. Yeah. So
Yeah, that's another factor.
okay, so these are Maxwell equations. These are experimental laws. My task is going to be to explain them to you carefully from the point of view of money. Everything has to do with money. It has to do with the measurement of effort, okay, or the measurement of quantity. So this measures effort. how much energy I have to put, or how much energy I'm going to get. This one over here, so here is effort. And effort is always related to money. Here is quantity. Basically, how much you are getting from your money. So starting from the left you pay. The right you get. Okay? So say that you're buying oranges. So you say, oh, I have to buy these oranges and put the money in that closed integral of h. That's money. How much of how much quantity I can buy depends on the cost of the oranges, right? But that's what it is. The left side on that equation is money, and the right side is how much you are buying out of current, or how much you're buying of a charge. So you buy current or you store charge. Basically, it's money here that you earn. Let's say this is your work. This is the money from your work. This is the money that you spend. And this is the money that you store. So your money, how much money you put in the bank, right? That is it. It's that simple. So forget about the formulas, forget about this thing. The effort, I call it, this thing, I call it the work integral. This is called the work integral. And this is a quantity. These other two things are quantity. That over here is a quantity. This is the money that you get directly and you can spend. And this other one is the money that you store. And that can be stored and restored, right? If you put money in the bank this month, you have a little bit more money to spend next month. Okay.
So can we just say that, like, potential energy plus kinetic energy?
That's what it would be in the end. That's what it would the end would be. That's why I didn't put Kirchhoff law, because Kirchhoff law is here. That equation is current Kirchhoff law, right? I have the current in and the current out in two paths, right? So that is Kirchhoff law. Ampere's law becomes Kirchhoff law, Kirchhoff current law. Faraday's law becomes Kirchhoff's voltage law. So I don't need to specify them in that way. They are telling me what they do, right? So look at the second equation. The second equation is also the same, right? This is the money. This is the money that you put. This is the money that you put, and this is the quantity that you get. Now, the other two equations are just, they can be derived from the first two equations, but I'm not going to go through the mathematical process of that. I'm just going to take the four. Some people say there's only two Maxwell equations and derive one from the other, do a lot of math and a lot of things. We are not going to do any math. So we're just going to take, we know that the magnetic flux is closed in itself. It doesn't have a beginning, it doesn't have an end. So that is represented mathematically by that. But it's this surface integral, or the area integral of V is zero. This means it's always going to be closed. I am going to go very carefully into the physical meaning of all this in the next class, right? But and that is expressed mathematically like that. Mathematically, in some coordinates, this will be the divergence of V equals to zero. I'd like to call it divergence. I don't want to go directly to the Nabla product. Nabla product, strictly speaking, only applies to Cartesian coordinates, but I will derive this equation. Hey, it's going to be even better. Next week, I will give you an exercise. I'm going to build some knowledge on what is the meaning of this work integral, surface integral, and be prepared to derive yourselves different tools, mathematical tools to measure things, in particular, quantity, work, quantity being produced at a point, total quantity. These integrals that you see here, that's what they are measuring. They are measuring quantity and things. So it's it's going to be very interesting to see what this is. All right. Let me see what else I have. So I want to leave this for next class because this is the beginning of next class is the time in which Maxwell equations will be completely demystified. I will explain to you very easily what is the meaning, interpretation, and thing of these equations. These are all experimental, so you need to come up with experiments. If you're going to teach a class on this, you need to decide which experiments you're going to put to demonstrate them. That and that. Yeah, those things need experimental validation. So the equations here in the integral form are very good to give you interpretation, and those are the ones that you need to validate experimentally. The differential equations, the differential on the left side, the ones I'm going to put now on red, these ones, this is the way to solve the equations. The ones on the right cannot be solved. They can be solved for very nice geometries. If you have a sphere, if you have a rectangle, you have a square, if you have a point, if you have a cylinder, you can complicate your life trying to do these integrals, and you will do them. And if you are stubborn enough, you will going to get some very nice solutions out of that. But the moment you deviate, the moment that you have, instead of having a cube like that, right? Now you have your cube with a bump, or you have a conductor that goes like that. That's it. That's the end of your mathematical simplifications. Can't do an integral this way. So the good thing is that Maxwell equations can be transformed into differential equations at a point very easily. Well, very easily with two basic concepts, right? Two basic concepts, which are the theorems, Stokes theorems and Gauss theorem. All right. So in the next few classes, I am going to transform these things. Next class is to interpret these things and get them into the others. All right. So any questions here in person or any questions online? Let me stop share so that you see my face. So, for the Mexicans, any comments? Fermin?
Yes, Doctor.
This is
Francisco, thank you very much. Only
this is-
one thing I heard that you mentioned that all insulators can be are dielectric materials.
no.
But not
The
all
other way around.
dielectrics can be.
All dielectrics is the other way around. All dielectrics are insulators, but not all insulators are dielectric.
Because I thought it's at
I said
reverse.
it. I said it the other way around.
No. You say it like that, but I understand that all the dielectric insulators are dielectric.
No,
Well, not all the dielectrics can be insulators.
no. The dielectrics are those materials that are capable of forming dipoles.
Dipoles, yeah, I understand.
Okay. Anything that forms a dipole cannot transfer the current, conductive current through its body.
Okay.
But there are materials that don't form dipoles that say don't absorb charge,
Mhm.
but they are low conductivity.
Okay.
So they can have a permeability that is permittivity that is around 1 or smaller than 1 and still not conduct electricity.
Mhm.
Yeah.
Yeah, maybe it's the confused because in the point of view of insulator high voltage, we say that all the insulators are dielectric, but not all the dielectrics can be used as an insulator because
Correct.
some are,
Correct.
yes. You know.
Yes, practically speaking, you are right. So, but not all insulators can be used as dielectrics either.
As the electric materials. Okay.
Yeah.
The electric breakdown.
So the other way around, say you have a dielectric that you cannot use as an insulator. Well, you can use it, but you may have to. You may need. It's not
Explosive,
ideal.
maybe.
It's not
Yeah,
ideal, right? There are two properties there. What is the conductivity? And the other is, as Carlos put it here, is what is the dielectric strength. So at what point this material punctures, and then therefore it stops being a dielectric, it becomes a damaged material, right? So let me find out a few materials that can be used as insulators and they are not dielectric, and the other way around.
Yeah, okay, thank you. I will do it.
Let's see. That will be a good thing to. It's non-dielectric if the permittivity is 1 or less.
When we need to install some insulators, so do we check the proper dielectric properties?
No, it doesn't matter. When you need to install an insulation, the dielectric property is not important, except if you have a system of insulation. Say that you have, say that you have paper, plastic, and oil. So in those cases, you need to make sure that the permittivity is as constant as possible, because the material with the smallest permittivity is going to be the one that is going to be stressed the most. So you need to, in an insulation system, the key of the design is that everything has about the same permittivity. Okay, so we will see those things. We can have an example. Fayaz is going to build some cylinders with different permeabilities, and we're going to see where the electric field is concentrated. Yeah, you see. So, so in an insulation systems, we try to keep the permittivity as uniform as possible in the different materials. But the important thing of that is the dielectric, the breakdown. What we call it, the dielectric strength. The dielectric strength is the important characteristic of insulation. Now, if you're talking about an insulator on a transmission tower, that is a more complex thing, because you have the field going through the body of the insulator and the field coming from the outside through the insulator chain. So things are a bit more complex than only trying to puncture the material. Yeah, these insulators, even those insulators, depends on how humid it is, how much dust they have collected, whether they are installed in an environment that is with salt, like coastal. So, and if they are high up in the mountains, because the air around them, it has a different density. It's a lot more complex than only trying to puncture the material. Yeah. It even depends on the shape of the conductor. If the conductor is round or is a point or is flat or is whatever. It's when you get into materials properties, it's a kind of fishy word. Yeah. Question Fayaz. You forgot it.
No, it's the polarization property of a material for a dielectric.
Mhm.
So if we are putting a dielectric, then the electric field response increases if it is in the capacity. So it's like if it is polarized molecules, or we can say atoms are polarized, then more opposite atoms appear on the plates, and then more electric field is there. So it's related that
I don't know. I don't think I follow everything you said. So repeat it, please.
actually the thing which you mentioned, that dielectric the insulators and dielectrics are not same, and dielectric is the thing.
Are kind of cousins. They are not the same. They are not twin brothers or twin sisters, but they are cousins.
So dielectric are the materials that can be polarized, whereas
Yes.
insulators are difficult to polarize. And then
No, no.
or no
Insulators are difficult to circulate current through them. So, dielectrics form dipoles, and the larger the dipoles, the more charge you can store in them. So dielectric is to manufacture capacitors. You can store energy charge. But insulator is to prevent the circulation of current, not necessarily to store charge. Store charge may be just a consequence of it, but it's not the important thing of an insulator to store charge, as it is important for a dielectric to store charge. Okay? So it's two different things. All right. Question here.
How common are isometric dielectrics?
Isometric? What is that?
That has like different values of because in magnetic materials it's very common, but I don't know.
If you have different layers, you have different behaviors in one way than in the other.
Mhm.
So if you have an insulation system with multiple layers, that absolutely is an isotropic immediately.
So it's more like a composite material that we.
Yeah, if it is a composite material, it more normally will be uniform, right, in all directions.
Mm.
Yeah, but if it is a layers of different materials, then it's a non-isotropic.
Like the same question, the anisotropic material in which you mentioned that you give the tensor, and I read somewhere that if the on-diagonal elements go zero, the material axis and coordinate axis, they are aligned. What like
Okay, say it again.
In the tensor thing, like
Uh-huh.
anisotropic material, where the material properties changes with space, right? So
No. Changes with direction. One thing is
Yeah.
homogeneous and non-homogeneous, which it changes with space. So it's not the same here than here. But that's not what I'm talking about when I say isotropic. Isotropic is the material can be homogeneous, but it doesn't have the same properties this way that way. The conductivity, for example, could be different in the x direction than in the y direction. That is when it becomes a tensor.
so there,
It has to do with the direction, not with the
space.
exactly.
If we go in a space, then it would be non-homogeneous.
If it changes with space, it's non-homogeneous. If it changes with direction, it's non-isotropic. And if it changes with the field, it's non-linear. Okay? All right. Thank you. Gracias.
Thank you.
See you
Gracias,
later.
doctor.
See you later.
Gracias.
See you.
Nos vemos
Gracias.
semana que
So the
entra.
next class
Gracias.
is the next,
Sí. Bye
the
bye.
next.
See you next week.
Bye.
Next weekend. Thank you.